All right, I think it's recording now. Okay, so now share. Yes, I definitely forgot. Can I share my whole screen? I think I can.
Oh, I know why.
What is it?
Your meeting ID requires password.
You guys had to have a password to get in too? Or?
Yes. When you send us that meeting link, meeting ID, you actually send us a password as well. I don't know.
I sent a password?
Yes.
Oh my God.
That's in that email.
Well, okay, I guess everybody got in, so they must have done it. Everybody did it but me. I've never seen that before. So does your screen look like, since I can't see what this looks like, does it look like this? Yeah. All right, so someone's microphone is on too besides mine. How about now? Yeah, good. Okay, so the APA guidelines, I wanted to hit that real fast because you know that part of what we do has to do with IRB and trying to keep legal and all those sorts of things. So I gave a link to the APA guidelines, and it might be worthwhile to for you to go look at those. But this is the bottom line, is that we've entered a time of, I think they're calling it the fourth generation now. It's gone past meta-analysis and the normal things we're doing, where the idea is that we share data online and archive so that other researchers who have different ideas or different theories or better ways of analyzing stuff can use that data. Of course, though, there needs to be guidelines, and so we follow the APA guidelines on keeping and sharing data that protects the confidentiality of the participants in our research. And so the paper that I'm going to talk about today from 2013, very briefly, is data that was reshared. It was a study that was done in Germany in German, and we published a second version of that, the one that I sent you in 2013. So if you have a chance to look through those APA guidelines, I don't think that since I want to talk about a whole bunch of stuff today, and I don't have a lot of time, I think I'll just let you read that on your own. If you don't mind, could you, if you have CMAP tools, I thought what I'd do is introduce CMAP tools again. Sudeep and Chuchin. And Sudeep, I don't remember, and Clayton, we did this last Tuesday, but so this will be a reminder for them. But I've created a map. I've created a CMAP for us to share on in CMAP tools, and so this document here shows you where it is. So if you have CMAP tools, head out there, and the goal of what this screen is about is so that you can find this folder, which is buried in millions of folders, and share it to your shared CMAP in places. Then from then on, all you have to do is click that one globe on the left, and that it'll be sitting right there. So the first step is you'll end up in favorites. So the first step is you do shared CMAPs in places. Those of you too that have access to Box, this PowerPoint is in Box. You click the third one down, which says public CMAPs number 3. Then you go down there, about 8 of them, to users. That's the number 3 dot. When you click on users, you get this one over on the right. Now this has 1,000 folders in it. So you have to scroll down all the way to LDT. You can see the little scroll by number 4, how far down it is. LDT 594. When you get to LDT 594, you can right click on it and add it to favorites. When you do that, then it will always be favorites, and you don't have to do all of this. It's a one click away. So if you're able to get there, I'm going to take the screen away in a second in case you need to see it. So anybody still need to see it? So I want to go out to CMAP tools. Okay, nobody's saying yes or no. So, okay, so I'm going to stop sharing. I'm going to go out to CMAP tools. Oh shoot, I thought I'd launched it already. I'll have to launch it. Have any of you used CMAP tools before? No? Long time ago, yeah. Okay, so over in favorites here, favorites, where is favorites? In favorites now, I've already got our LDT 594, so I've created 2 folders in there, and the one that I think that, I'm gonna open one, but we're all going to open for note-taking today, but let me open the demo first just to show you a few things. And I probably need to share my screen too, so let me go back to here and share my screen, and and share. Okay, so I just opened, I forgot you didn't see what I did. So what I did was I clicked on favorites, which is over here somewhere. I came up to LD2594 and I clicked this. So what I want to show you is real quick, is this what you see, Grace?
Yes.
Okay, great. Okay, so what I've got here is a CMAP that I've started. I've got like the introduction, topic A, 1, 2, 3, topic B, 1, 2, 3. So I'm going to go ahead and paste in topic 3 real quick. So I'm just going to drag over, copy, come over here, paste, drag it over, change these to C, oops, C, and you get the drift, C1, C2. I'm just doing this to just give you some ideas here, C3, and then I'm going to connect this. Here's the catch on this. If you click this arrow and, whoops, if you, when you're using CMAP tools, if you click on it once, you get this double-headed arrow and you can drag it like this. If you do that, you'll get this box in the middle. That's where you put the is-a, has-a, goes to. In other words, we put nouns in the concept boxes or in the note boxes. We put verbs in there. Those always look ugly to me when you make a network map like that. So what I prefer to do is when you click on it, take your finger and hold down the shift key and then draw. And don't let off the shift key. Hold your finger down on it until you let go of the mouse. And what that does is it draws a line. So now we've got a CMAP here. Topic A, topic B, topic C, 1, 2, 3. And one thing I wanted to show you real quick is if I expand CMAP tools, whoops, right here, and synchronous collaboration has been enabled, that's good. And all these maps are in the way. Whoops, I clicked the wrong thing here. What I wanted to do is click this. All right, so if I click the word called CMAP outline, I want to show you something. I've got introduction and I've got the thing that your English teacher told you to do, which is to have 3 main topics, A, B, C, and under each one have 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. And then the conclusion. So let me say this again. I didn't draw that outline. I drew a concept map over here on the left-hand side, but when I click this tab right here that says outline, it gives me an outline. So in your brain, I want you to say to yourself, a concept map is an outline. An outline is a concept map. They are informationally the same thing, okay? There is no difference. And so that's what we're going to find out a lot about the data today, that we're going to talk about nodes, pairs of nodes. Well, this concept map is also a whole bunch of pairs of nodes. It is that. And just with those nodes, I can regenerate this concept map completely. It's completely sufficient to regenerate this concept map if I just do nodes. So that's why a lot of the software that we like to use for network graph analysis doesn't like this structure. It likes pairs of terms, pairs of nodes all the way down. So let's just, if you are willing to collaborate with me, let me close this one and let's open, let me go ahead and save it. Any questions about that? But an outline. Let's go to 4 note taking today. And I am going to click the share button. And what we're going to try and do is collaborate with each other. And what happens is, I think if you click the share button, it's this little pencil here. If it's got a line through it, that means you're not sharing. So if you click through that, then it should start sharing and it'll ask me if that's okay because I'm the main person. So did someone click on it or does anyone have CMAP going? If anyone has CMAP going, do you have it going? Oh, there's somebody, and I will say collaborate. I don't know who that is, but whoever you are, go ahead and put something out there. Click and just double click and it'll give you a concept map like that. Yeah, there it is. That's Mitch. I don't know who Mitch is, but there you are.
It's Lee. He's catching my last name.
Okay. Okay, Mitch, try doing that arrow thing. You know, try and draw. I clicked on yours. Try and draw a box and then let go and see if you can do it without creating that stupid that you did it. Success. Okay, very good. Okay, and so the idea is that, you know, while you're doing that, I can also do it. So we're all, but I didn't do it as well as you did. I got the stupid somebody else, so allow. Let me delete that. Let me delete the one I just did because I didn't do it right. Yes, allow. I'm getting a lot of people that allow here. A couple more. So anybody that can, just go ahead and just start. We want to see us all clicking around here. There we go. And I can see who that is. Is that Jing Chu? It looks like. Yeah. So you just, whenever you get a box, you just put it in and you just type whatever you want to in there and so on. So this is a study that actually Jing Chu is doing. She is reviewing videotapes of online collaboration of 3 people who were using this tool online, an IST 110 course, to generate a concept map of the entire chapter. So she's watched about 12 videos of teams doing this, and we're not going to talk much about that, but this is the tool they use. And once the concept map exists, then it's easy to convert it into the kinds of tools that we need to do the descriptive analysis of the tools without having to do any manual labor for scoring the maps. So you get the any questions about this so far? There is a tool here. Let's see what you see. Do you see that tool? I think I'm sharing my whole screen, aren't I?
Let me see. This one. This is what.
Good, yeah, you're seeing what I'm seeing.
Yeah.
All right, so this tool right here lets you do lots of things. Real quick, like for instance, let me click on this, and so I can go to line and say no line. And so now there's no line. I can click on it again, and I can go out to the object and say no color, none. You get what I'm saying? So this is a term. This is the same as this. It's just that I have complete control. I can change the color of it. I can go to font and change the font style, or I can change the font color. So one thing I like to do with CMAP tools is because it saves itself, then, and I like to use these kinds of CMAPs in publications. And sometimes I need to have 2 maps that are aligned in the same way. If I save it as CMAP tools, it's easier to do mapping here than it is to try to do maps in PowerPoint, because PowerPoint doesn't let the connector stay connected. It doesn't center. This lets me do everything. Color, I can change the font, I can make it bigger or littler, put whatever I want. So I use CMAP tools not only for collaboration research, but also for my own drawing of maps. So any questions about that? So you can imagine how this could be used in all sorts of ways. So if you want to just keep taking notes, that's okay, but you don't have to. I'm going to go ahead and go back and drive through my PowerPoint now if I can. So do you see a PowerPoint slide now, everybody? That says big. Okay, so here's the big picture. I have 2 slides. The idea is that inside somebody's head is a situation model. It is a knowledge structure, okay? This is not news, okay? And the idea is that in terms of activity theory or any cognitive theory that has to do with this kind of thing, that you're doing something, a human doing something, activates that situation model and overlays it with, the structure of whatever it is you're doing. I've got a whole pile of papers there that looks like a poor old doc student's trying to get through a dissertation there, reading all these articles. But the idea is that it contains structure. And so she's got structure, it's got structure. They align or they don't align, but the idea is that structure in that document, it messes with her head, okay, to produce the updated situation model on the right. So this is the big theory, okay, the idea that everything has structure, every information piece has structure in it, every conversation, everything you read, every video you watch, every picture that you look at, everything on earth that's information has structure to it. You have structure, and they either align or they misalign, okay? I dragged this out of one of Hay and Kitchen's articles. Kitchen is one of those people in England that does a lot of research with, he's an old guy like me. He's done a lot of research with concept maps. So I like to pull his stuff out. He has a very different usefulness of concept maps than I do, but take a look at this real quick. His concept here that Hay wrote about is that at the top, we have the expert knowledge of the teacher. So just like I said, they have a situation model in their head. They have to turn it into a lecture. So that's over here at point 1. A lecture by its nature tends to be linear, okay? So the idea is then that the students down here, the novices, they pick up some of those black boxes, and they have some of their gray boxes they had already. And there's 2 ways of doing it. One is you're emerging with meaningful knowledge. In other words, this one down here begins to look more like the one above, or you just memorize it. If you memorize it, then it looks like the sequence of the lecture. That's what we would call a linear structure or a sequential structure, and that's how we usually define it in the articles that we write. Whereas the one on the left, the emerging, would be the relational structure. And so what you're seeing with the relational structure is more node degrees. Like up here in the expert, we see this node has 1, 2, 3, 4, has 5 links. All of this is centered on the idea that some terms are more important and more central. They tend to hold the structure of the knowledge together, and those are the high degree nodes. So I put this article in our box folder in case you have any use for this, and I'm going to refer to another one of theirs later. But I won't even hit this, but I'll just point out some things that concept maps can do. I know that a lot of you aren't doing concept map research, but it doesn't hurt. It's where I got started with knowledge structure, and so it doesn't hurt to get the idea that there are lots of uses here. It's about memory, about structure, higher level thinking, synthesis, creativity, beliefs, values, and so on. So I wrote down at the bottom in red that this is alt data. Okay, so a lot of research is not alt data, but the way we think of it, it is. What we're saying is that our representation of concept maps as knowledge structure is outside of the mainstream of educational psychology or cognitive research. I'm not even sure if it aligns with the learning sciences as well as it could. So whenever you're adding this to your dissertation, these measurement approaches, you either have to frame it in the format or way they talk about it, or you have to clamp it on to something you're doing that is a whole all by itself. You get what I'm saying? If you just come out with knowledge structure as we're presenting it as a theoretical model, it's going to be pushed back because there isn't literature on it. So it's alt data. It explains a mediating process between the structure that exists within the learning materials that you created and the structure that exists within the learner's head. And of course, you can use concept maps in tons of ways, and here's just a couple of them. It's assessment, before class, after class, during class, small group, individual, whole class. You can do it where it's a partial map or a whole map. You can do it just individually to organize your own research. Some people take notes when they're in. I took notes one time when I was taking a stat course as a graduate student. I did it as a concept map. It was extraordinarily helpful because I was able to get 3 or 4 lectures worth of information into one concept map. And when I would refer back to that as a new lecture was going on, I'd say, wow, okay, I'm seeing things that I didn't remember from the other lecture that are having a higher priority. And now we're talking with Chu Tian about using in a debate class where we literally would hand out an expert map to a debate team so that when they're debating, they can look and see where their advocates or the people who are against their position, where they're arguing in the map. And hopefully the idea is it would give them insight into how the argument is going along so that they could counter that argument. So we're thinking about ways of doing this with in China. So why do we use nouns with expository text? Well, a lot of research, decades and decades of research, summarize what Elman has here with neural nets is that it appears that nouns and verbs tend to gather together in our knowledge structures in separate places. And not only that, but even nouns cluster together within types. In other words, if I give you a series of recall tasks, you'll tend to have cat and mouse together more often than you will cat and plate. The reaction time's better, the free recall's better. In other words, the structure of your knowledge is sort of like the way this looks visually. That's another advantage of concept maps, by the way, is that, it helps us to see the knowledge of our structure, okay? So this is just an example to try to help understand why we're using concept maps. Also, with expository text, we use nouns. And the reason why is because expository text is really boring, okay? It's science text. Most of the verbs there are things like is a, this is a this, that has a that. It's not like, the dragon, killed or kidnapped the princess. Kidnapped is a verb. That's a very important word. But we don't ever say like this collaborative group kidnapped, the artifact. That's not the way we talk about expository text, okay? We would say it's a component of, or is, or has a. So nouns are critically important in expository text, but I have a feeling, though we haven't done much narrative work, that verbs are going to be very important when it's a story narrative. So we need to keep those things in our head. It's that the way we're doing things is focused within a very narrow domain. If we're expanding it into narratives or other genre text or thinking, then we probably will use different parts of speech. Part of this has been validated by the eye fixation research that Lindsay did recently of turning eye fixations into concept maps. So what she found is that even with expository text, the students who are high capable comprehenders tended to focus more on the nouns that were in the expository text, whereas the poor readers focused on a lot of auxiliary words. the nouns and auxiliary words. So literally, if you're a good reader and you're reading an expository text, you sort of are able to smell the nouns. They sort of light up in front of you as you're reading, and you grab onto them, you fixate on them as you're reading across the page. You have this built-in thing inside of you that directs your eye gaze so that you're reading certain things when you're reading. And we don't all read the same things, don't get me wrong. When we put a text in front of us, we all assume we're reading the same thing. The eye fixation literature and the data that we've looked at is very clear that even though it's the same text, we don't all read it the same way. So it is the way it is, but when we read it, it's very different. And so we're doing those kinds of measures. So again, nouns. All right, so this is the study that we did. I'm gonna blast through 5 slides real quick. The reason why I'm showing you this one is because it shows you a really easy way to turn concept maps into data that you can analyze without having to do all the gyrations without a reader or with doing Pathfinder Network or any of those things. This is a really easy data from map to data that you can do something with. And so here's the study. It's this is about problem solving in teams. There were 120 triads, so that's 40 teams that were working online. Half of the teams were assigned to hidden profiles and half were not. A hidden profile is when you give people part of the information and you tell them you've only got part of the information. The other group received all of the information. It was the topic was about there's some beetles or something were killing forest in Germany. This is a German study. And we were looking for a pesticide solution that would kill the beetles, would solve the problem without damaging the ecosystem. And so there was enough information in all of the data to solve the problem. But in the one-third condition, there wasn't. So the idea is that if I know I don't have all the information, I'm going to try and drag it out of my other partner so that we could come up with a solution. So is that pretty clear about what the groups were? Okay, so here's what the experts map looks like on the left, the fully explicated map. And on the right-hand side is the solution. That's all you need on the right-hand side. It is a complete subset of the expert. Here's how the data goes. All you have to do is write down the node or the concept and count the number of links to it. So for instance, construction spruce on the left-hand side has 9 links. Whereas on the right-hand side, construction spruce only has 6. So that is the data collection. You simply lay the map down in front of you and you count the nodes and it produces a vector. That expert vector has however many elements that is, 12 or 15. The solution vector also has 15. Notice the zeros. If they don't include something, you simply code it as a 0. Now, what in God's world are you going to do with that? Well, we're going to do a couple of things with those. One thing is 2 columns of numbers so we can correlate them, okay? Another thing we can do is those are node degrees. And node degrees are, it's possible to calculate various graph metrics out of it. We can literally calculate metrics that describe the shape of the one on the left and the one on the right. Okay, so question so far, do you see how easy that is? I mean, yeah. Oh, by the way, if you put this map in CMAP tools, we can generate these kinds of data. All right, so real quick, let me finish the last few slides of the findings. So here's what we found out. We compared the group maps to the expert, to this expert, and to the solution map. And here's what we found out. We found out that the people who received, the teams where all 3 people got all of the data, their expert map was less like the expert. It was less like this map. And their solution map was more like the solution map. Now remember, they've never seen either one of these, but their solution, in other words, they were able, their map, the map that team drew, looked more like a solution. It got rid of stuff that didn't belong, and it kept the things that did belong, and it kept the things that should belong properly connected to each other in terms of node degree. What about the folks down here that got half the data? Well, what happened is that they were more like the full expert. They looked more like this, but they looked less like the solution. So let me try to say that one more time. Or you tell me, does that make any sense to you? Can you explain that to me? Or did you all go to sleep? If you have any questions about the data, go ahead and ask that too, because it may not be clear.
So what is the word here? Old data when working, and what's the next one?
The one at the bottom, yeah, it's not very clear, is that this is in the way. The control group, they each had 1/3 of the data. So and remember, this is a group map, so they derive these maps together online. Okay, so what does that tell you about when you only have part of the data? What happens? What kind of map do you design whenever you're only given, when each of you is only given part of the information?
So can you say which is better?
Okay, well, that's a good question. Which is better for what?
For a certain question. So they must have had some research questions. They must have to solve some problems.
Yes.
So yeah. So
Yes.
in that point of view, which research make things better? I mean, drawing the concept map together with others.
Okay, remember they all drew a concept map as a group. So the question is, whose map? You're asking whose map was better? Well, their goal was to solve the problem. So the more it looked like the solution map, the better.
Okay.
Yeah. So the treatment group, the not interdependent group, that is, everybody had all of the information. Their solution was better. But what if that's not what we were interested in? Not can you solve the problem, but can you fully explain or account for all of the issues involved?
Okay, then the first one.
Then it's the first group. It's better to let everybody have part of the information, right? So it depends on what our goal is, which is better for what. Now, what we found out in this study and in a study that Kyung Kim did following up is that we found that there was a timing difference for these two groups. The group, when everybody had all the information, they only spent 3 minutes generating and brainstorming ideas, and they immediately spent the next 15 minutes drawing that solution map on the right. In other words, they, instead of putting it in the map, they did it in the air, talking to each other, focusing and converging on the solution. So they went from divergence to convergence very, very quickly. When you think you have the answer, you don't spend time with your group trying to get information out of them. You just tell them, just be quiet, I'll draw the map, okay? But on the left-hand side, the big map, if I don't have all the information, and I know I don't have all the information, I spend extra effort in the group getting people to tell me. And when they tell me, we put it into our map. So can you say back what I just said? What about you, Grace? You get it? I see you're squinting, thinking about it. Your brain, I see the gears going around.
So when they have all the information, and so they have the answer quickly, so they don't spend a lot of time trying to find what the answer is.
That's right.
So they spend more time trying to construct the map that's what the solution should be.
Yes.
That's what you're saying.
Yes. If you think you know the answer.
So they don't spend a lot of time doing it.
And if you don't know the answer.
If they don't know the answer, they'll spend a lot of time trying to construct a map and then not working toward what the solution really should be.
Yeah, so then the question is then there was a question after they drew the map that said, so what is your answer? And both groups got the answer. Okay, pretty much. So you can look you can read the article and see, but either of these maps generates a solution. But the one is faster than the other, but there is a potential problem. The potential problem is when a group is solving one problem, they are more efficient and they find the answer faster, but then there's a term in this in engineering called the answer is brittle. It means that it's a very rigid answer and it solves this problem, but then if I ask them another question and I change it and say, but what about if this happened? Well, their map is insufficient now to answer that question. Are you with me?
Yes, but what exactly is the goal? When we want our student to have a concept that's closer to the full expert rather than just partial of the solution to that question.
Anybody have an opinion about that?
Yeah, I felt if it's vocational school, the second map should be better because they need to learn.
We're going to procedural solutions. There is a protocol that we all need to follow. There is one good answer, and that's what we need to focus on. Okay, keep going.
Yeah. Would you say it again, declarative?
I guess you could call it declarative or procedural knowledge, perhaps, yes.
Procedural knowledge.
Maybe even if you think back to Hayes's diagram, maybe it's memorization in a way. But I mean, they didn't memorize this. They just came up with a smaller map that was solution-oriented.
So right side is procedural, but then left is declarative.
Right, perhaps. Oh, no, the left side is relational.
Relational.
Okay. In other words, my imagination is that the one on the left, the big map, you can solve many problems with it.
Yeah, I believe so.
Right.
The one on the right, you can only solve one problem with it.
Right.
Maybe one.
So
Now-
that they actually get a fuller concept or more complete concept if they are able to come up with this
Right.
left-hand side map, isn't it?
Yes, that's what the data is showing here. But again, you know, it's what's your goal as the instructor or what's your goal as the instructional designer. You know, if you want them, I don't know if you recall, but we've talked about this before. In the area of generative learning, these are examples of generative learning. Whenever you allow people to do generative learning, it's often at the expense of declarative knowledge. Let me say it a different way with a practical example. We had some research that we did in the medical school where the focus of medical school is to super memorize stuff. Like super memorize, not just memorize, but super memorize it. So it's more like the left-hand side. It's like, this is the way it is. And so when we brought concept maps in for them to look at, they would discuss the concept map of the topic. Let's say it's the endocrine system together. And at the end of that, they would all look at each other and say, I understand this for the first time. I could pass the test and make 100 on it in terms of what does what to what, but it was just memorized declarative knowledge. But when we talked about it, all of a sudden I understand how this part of the endocrine system fits with this part of the endocrine system and how this drug has this influence on this side and this influence on this side. So they said, I got it. It makes sense to me. Does that make sense to you, what the concept map did? However, they didn't do quite as well on the test. So there is always a trade-off between the left-hand and the right-hand side. If you have to super memorize something, then you have to be careful with generative learning approaches because it has to release some of the dimensionality in order for the network to form relationally. We're talking about higher dimensional structures that may compete with each other, that if you have it this way, you can't have it this way. If you're going to take these two things and put them together, something has to give a little bit of slack. So the alternative for them is to memorize these things as independent silos. Then they have very strong declarative knowledge that does very well on multiple choice tests. But if you want them to truly understand it so that they're at a level so that they can do what? So that they can do diagnosis. You gave me the drug and it didn't work, why not? Well, what we're going to hope is they move from this silo to this silo, but what would be better if they actually understand what's going on. Okay?
But
so, all capsulated here. Yes, who is that? Go ahead.
Yeah, but like, do you think it's possible for students to have both structures parallel existing?
Yes, if we look at fuzzy trace theory, the idea, yes, that's what you were thinking, is that there probably both can occur, and that it's worth it to give up a little bit of declarative knowledge in order to form a richer expository structure. And also remember the way fuzzy trace theory works is that adults prefer gist, adults prefer relational, adults prefer the one on the left. Whereas children seem to be unable to do that except for the highest level of children. And so they're almost always linear. They're almost always getting things in chunks, in silos. And when you ask them to, if you ask a child to recall something, they jump into that silo and they tend to repeat it sequentially from the beginning to the end. But when they start reaching 3rd, 4th, 5th grade, their internal knowledge structure, their situation models for the content are starting to become more relational. They're not siloed linear structures anymore. They're starting to get chopped up into chunks that are larger and make more sense. So now it's a puzzle. It's these silos are breaking down and they're starting to be able to integrate into relational structures. They're starting to understand whatever that word means. That's what they're starting to do, okay? Now, what is the advantage of that again? Well, if you have brittle solutions like the one on the right, they're very good for solving some kinds of problems. If you have a relational structure on the left, it's very good for solving some kinds of problems. They're not necessarily the same kinds of problems. So you have to make a decision about those kinds of things. Okay, so so far so good. Let me talk about issues now. So how did we compare? Where did this column on the left side of this that says the mean coefficient of determination? What in the world is that a measure of? This is why we're doing this PowerPoint today, by the way. Well, here's the way it works. Remember back here, I said there was a vector here and a vector here. So if I correlate these two together, I'll get an R value. In other words, just correlate the two, R equals something. Well, if I square that, that's called the coefficient of determination, R squared. And what that is it explains the percent variance explained for the correlation metrics. So that's what we did, was we correlated, remember, every single team has a vector that looks like this. They have a node degree vector. Remember where the node degrees came from. All we did was count the number of links and put it into this table. So imagine 40 teams here, plus the experts, 40 of them. So all I have to do is correlate the team to the expert and the team to the solution, and I'll get an R value. Square those, and I've got the coefficient of determination. There's the R squared. Once I've got that, it is normal interval level data, and so I can average them, I can do ANOVA to them, I can do all sorts of things to them. And it worked out okay in this study because all the correlations were positive, but it's conceivable that a correlation could be negative. It could create problems. And so we moved away from using the coefficient of determination, and now we're using Fisher's Z. And you can read what Fisher's Z is. It's not Fisher's Z, it's not the Z standard deviation. Fisher's Z is a metric that converts R values, which are not interval level data. R values, Pearson R values, are not interval level data. But if you square them, coefficient of determination, that is interval level data. That's why we didn't just use R values. You cannot average R values together, because the difference from an R of 0.2 to an R of 0.3 is not the same as the difference from an R of 0.7 to an R of 0.8. In other words, an R of 1 change, the scale is not consistent across it. It gets bigger as the R's get bigger. But when you square them, it is interval level, and you can do that. But we decided to use Fisher's Z because I don't know why, we just did. So some of the studies, you could use either one, I suppose. So are you with me why we're using coefficient of determination? We're getting R values out of this, and we can't do stuff with R, so we use R squared. So that's why. So that's how easy it is. If you got a whole bunch of maps, all you have to do is decide on what the nodes you're going to count are, create a table of the names of the nodes, that is the names of the nouns, and just label at the top, group 1, and just count the links. Boom. You've got an Excel spreadsheet. All you got to do is dump that in the SPSS, generate an R, just do the Pearson R's. You got them all. There's your data set. Now, here's one other cool thing about node degree vectors. Node degree vectors can be analyzed with multidimensional scaling. I showed those little arrows pointing in there. When you think of node degree vectors, what you should be thinking about is that they're pointing out into a dimensional space, and that there's a word sitting on top of those arrowheads. So really, when we look at this diagram that says dimension 1 and dimension 2, really what's happening is that somewhere in XYZ space or wherever it is, there is an origin, and these are all things we're looking at, and they're setting on top. There's a word setting. It's like if we're looking down at a forest and there's words setting on top of the trees. And the trees may be different heights, but we're looking down and we're seeing these words. And so we don't realize there's a tree under there. All we realize is there's a word just hovering there in space. So that's what this diagram is. So let's take a quick look at this. So what we're seeing here is, on the left-hand side is the vector for the full expert. It's at 0, 0, and -1. Everyone asks, what do dimensions mean in multidimensional scaling? The answer is, you can't know for sure. The way multidimensional scaling works is it's essentially like factor analysis. And so it's sort of like you could do a factor analysis of the same data and it would come up with factors. And so you say, well, what's the name of this factor then? And the answer is, well, I don't know, but you ask yourself, so what went into it? and then you look at what that is, and you could name the factors sometimes based on the things that factored under it. But I like the dimensional representation better. And so what we see here is these blue ones. Let's remember what the blue is. The blue is they were given part of the data. And so what you see is these blue ones with the C in front of it, they were given part of the data. Their group maps are closer to the full expert. And what you see with the red ones, that was the ones where everybody had all of the data and they went to the solution real fast. You can see that they're like the solution map. Oh, and by the way, this is the data they were given. The people who were given only a third of the data, they were given either expert A, expert B, or expert C. So what could have happened is that these blue ones could have hovered around A, B, or C, because that literally, if one person had dominated the discussion, which may be what happened with CO3 up here, maybe one person who got this data, that got expert A information, drove the discussion and wouldn't let anybody else talk. And so that's why their group map looks like expert A. And over here, maybe in group C21 and C20, they sort of look like B and C. Maybe the same thing happened. So in the analysis of the group discussion, you could look and see, did it seem like one person dominated? And if they did the map look more like the information that they brought to the table? And let's apply this as a generality for a second. Anytime that you're in a collaborative group, you sort of have this knowledge in your head about what it is you're talking about, and the other people in your group have the knowledge too. And if you overlap, then you're going to come out with common stuff that looks more like the expert. But if not, then hopefully what happens is you share data and you enrich the group knowledge. But if one person dominates, then it's going to look like their ideas. And so we're always interested in pieces of knowledge flow from a pre-map to the group map to a post-map. And we saw it with the CAS 250 data, that what happens is in the group where I have everybody in the group has all of the information, I create my map before I get to class. I work in the group and I don't share everything. And then when I do my post map by myself later, it looks more like my pre-map. In other words, the group didn't influence me very much. But whenever I haven't been given all the information and I'm told, the person in the group is told they haven't been given all the information, what happens is they have pieces of information, almost all of it ends up in the group map, and then almost all of that ends up in their post map. So literally, there is this thing where the collaboration works if the people know that they don't have all the information. But if they have all the information, it doesn't work. Someone becomes bossy and drives the, go ahead, what were you going to say, Grace? Yeah.
No, I agree.
Yeah, and so my imagination is there's two things potentially going on, is that one thing has to do with literally they don't have the information because we had hidden profiles and we didn't give it to them. So maybe it's because really they don't have it, that's why that happens. But I'm thinking to myself, maybe it's got more to do with attitude than it does with actual information. That if someone, right, you're thinking the same way I am, that if I come to a group and think I know it all, then I'm just not going to listen much. I'm not going to be very engaged in the group. I'm going to say, yeah, that's okay. I'm just going to give a consensus opinion. I'm just going to agree. But I'm going to go ahead and just keep my original structure and say, I really understand this better than those guys in my group. And so my post map is going to look like my pre-map did, okay? And so I think you can trick a group by telling them that I gave all of you different information. So even if I think I'm really smart, when I get to the group, I'm thinking, boy, maybe they gave Grace some information that I actually don't know because it was given to them by the instructor. So someday I want to do a trick study where we give everybody the same information, but we lie to half of them and tell them, I gave people in your group information that's critical to the solution that I didn't give to you. And let's just see what that does to their maps then, that it's an attitude sort of thing. Also, though, there are ways of measuring people's attitudes ahead of time about their perception of their own capability, their own self-efficacy, their own prior knowledge of the material. I mean, there's probably a whole realm of constructs that would help us to understand if people are coming to collaboration, these kinds of attitudes, okay? It's potentially an attitude thing. So these are no degree vectors. Now, if you think about it, the blue ones are over by the full expert and the red ones are over by the solution. If we go back and look at this data, this says the same thing, that the blue one here is near the expert and the red one is near the solution. What I'm saying is that all of this data is just different ways of saying the same thing, that this visual representation if we actually looked at the correlations, we would find out that C19's R value is more like the full expert than is CO3. Literally, the R itself that we would see for CO3 to the full expert is a reflection of this image that we're looking at. So R is this, or R squared, either one is the same as this visual representation. They're all interrelated to each other. Okay, so with nothing but stupid node degree vectors, nothing but this data, these columns of data right here, we were able to come up with this chart and with this chart. Same exact data that we just got by making a dumb table, okay? Now, one other bit of data in this study is something called graph centrality, and it's led us to where we are now. So this is the precursor of graph centrality. So take a look at this just a second. This is the same Hay article that I showed you at the beginning. Hay talked about, they looked at basically what happens. Kitchen has spent his life looking at concept maps. And after a while, he said, I can look across the room and tell you how the person is thinking about a topic just by the shape. If it's more spokey, it's one kind of thing. If it's more linear, it's another kind of thing. And if it's more networky, it's another kind of thing. I can almost, he said, I can almost grade a map by just looking at it without even reading the words. He's got that so deep in his head that that's where he's at. So here are the levels of hierarchy that describe a spoke, a chain, and a network. Here are some things that go with it, okay, about structure and so on. And by the way, this isn't unique to cognitive psychology. If you look at the physical network topology that engineers use to describe things like an electrical network or a computer network or any kind of a network, they look like this one on the left-hand side. So I put a link to Wikipedia to physical network topology. These are the general ones that engineers have defined. But even before the engineers defined them, the mathematicians had defined these in the graph theory, which is probably an area of mathematics that's 100 years old, okay? The mathematicians were thinking totally outside of any particular context. They're just imagining, a mathematician just throws things in there and says, what does that look like and how can I think about it? And they come up with this, well, it's possible to look at it like this, and here's the way I would do it mathematically. So the mathematicians came up with lots of ways, before we ever knew it was even useful, of how to measure networks. In other words, how can I, when I've got a spoke, what do measures look like? What does it mean? What are the implications of that? So far, so good. So this goes back to Ellen's study. We were, no, I'm sorry, I think it was this study. We were saying, okay, is there any way that we can look at network topology like Kitchen and Hay are talking about and measure it? So we came up with this measure. We said, if I use Freeman's graph centrality, which is a measure of the centrality of the most central node, the betweenness measure of the most central node, that's Freeman's graph centrality, I can calculate for these four kinds of structure, chain, hierarchical, network, and spoke, a measure that varies from essentially 0 for a linear structure to a 1 for a totally relational structure. Now, back here, when we look at Hay's ideas, we see the same thing. Here's the hopes, here's the spoke, here's the chain, here's the network, okay? And so the conceptual typology, Kitchen and Hay have defined it saying that it's the more central ones that are representative of better structure, that are more apropos for solving certain kinds of problems, and that the one on the left is, the linear one is more goal-oriented, whereas the spoke and star on the right is more, represents a naive epistemology. When you got a spoke and star, what it means is the student is fixated on one concept, whether it's the right one or not, they're fixated on it, and they tie everything to that one thing. So this is naive on the right. This is pretty goal-oriented, or I think that Min was saying procedural or declarative-oriented, sequential, you know, on the left. And this is relational in the middle. And so we can take any network and calculate its graph centrality that's between the centrality and come up with a numerical value that represents, that describes that network mathematically. And so that's what we did with these is the partial, okay, so let's see the full map. The full map has a graph centrality of 0.41, so it falls in this general vicinity. The solution map is a little more linear, but still pretty relational. It falls in this area. The partial maps A, B, and C all had, because they were exactly the same in form with just different words, they all had a graph centrality of 0.35, which is a little more linear. Then the interdependent control triad maps were even less linear. And then the triad, the non-interdependent, that is the people who were solution oriented, who had all of the information, they were even more linear. And that aligns with what Min was saying too, is that they were trying to come up with a linear solution. And they were more linear then, whereas the full expert, the fully explicated map was out here. And so the interdependent were more like the solution, but not fully out to the right. So that was what is in the paper that I gave you, the 2013 paper, is that, so we looked at node degree as a measure of relationship that we did inferential statistics on. We used node degree to represent as a multi-dimensional scaling so we could think about it in visual terms. And then we also did graph centrality to talk about it that way. And one thing that
I got a question.
Yeah.
The previous one. So this control triad map, wasn't it closer to full expert than to the solution?
Yeah, it was closer. Yeah, in the multi-dimensional scaling, it was quite a bit closer, but it wasn't fully expert. In other words, it's closer, but not full.
But now it seems like solution is closer to full expert, but
Yep.
I thought that
Yep.
control was even closer than solution
Right.
to the full expert.
Right, so it's possible, okay, so let's think about the rarefiedness of the data. Remember that this data here is coming from this very rarefied data, okay? Now, so it's one measure, but the graph centrality measure we're looking at is an image of the way it looks. So what this data is saying is that the solution map looks more like the expert map. In fact, if we go back, we'll see that it's actually a mirror image. This map, this solution map, actually lays right on top of this map. They are literally mirror, they're not mirror images. You could take this one on the left and delete the words that aren't there, and this will be identical to that. The central most structure is a construction spruce, and it's construction spruce here. It's just that some stuff is missing. So this representation, this one and this one, are based on node degree, which has a lot of zeros in it. This one is based, the centrality is based on one thing. That is the number of links to the most central concept. In other words, this is what I've always said about constructivism. Let me take a step back. Constructivism says that when we want to know something, that really you can't just have one view of it, that you've got to look at it from multiple perspectives. And every time you look at it from a different perspective, you have a different view. So both are true at the same time. That in one sense, with one way of looking at the data, we can see one set of relationships. But now when we look at the actual shape of the network, its form, then it's like this. It is more, let's go to that one, that the solution is more like the full expert. They're not the same, they're slightly different ways of describing the same data. They're both true. I don't know how to reconcile the two, but they don't necessarily overlay on each other.
And in that figure with the two lines, the red and blue line.
Is it this one?
The one, no.
Go back.
Go back.
This one?
And even one more back.
This one?
Right.
Yeah.
So does that slope indicate anything at all? Or good, bad, that kind of indication?
No, the slope itself is an artifact of the figure. Really, I could have drawn these with bar graphs so we don't see a slope from one to the other. All this chart tells us, the reason I drew it like this is because the ANOVA had an interaction.
Okay.
And this is the way I typically show interactions. And so what this chart is basically telling us is that blue is high with this one and red is high with this one.
Okay.
So yeah, that's why I drew it like this. Right. So that's another thing about charts and graphs is you have to be careful that the representation formalism itself, that you don't overinterpret it. It's the same with analogies, that you can only impress an analogy so far and not so far. But I like the way you're thinking, Grace. Is the slope important? Sometimes slope is important. If the metric along the bottom is meaningful, then the slope is important. In fact, let's look at an example. Okay, here's an example. The graph, the numbers along the bottom and the numbers along the side are meaningful. The numbers along the bottom are graph centrality, so that's meaningful. and the numbers along the side are meaningful. That's the test performance. What you should get is a linear relationship. That the better the graphs, I don't know if better is the right word, the higher the graph centrality, the higher the test performance. But the reality is that that's not the way this data works. That there isn't, as one increases, the other increases. What happens is there is an optimum value. That there is some graph centrality that relates to maximize test performance, and if you exceed that graph centrality and start becoming more spoke-like, your scores start to go down again. And we've seen this to be, this is an odd thing, we've seen this to be more true with Korean students doing activities than when Korean students are working in English. And also, it tends to be more true with Korean students than it does with English students. And English and Chinese students seem to be about the same, that these curve, it isn't as pronounced. I don't know why it would matter. However, there is a good likelihood that the Korean language knowledge structures are somehow fundamentally different than English and Chinese. Even though English and Chinese are so different from each other orthographically and, of course, phonetically, there seems to be more knowledge structure similarity between the two languages than there are with Korean. You would think that Korean and Chinese would be more alike, but it doesn't seem to be with the metrics we're using, not with the ordinary metrics that people in ESL or in language studies use, but with the metrics we're using of knowledge structure, that seems to be what's going on. It's crazy. One thing that I might suggest is with the study that we did with narrative and expository text, we saw the most profound difference for narrative with Korean. And it seems that expository text, as it spreads out, the form of expository text spreads out across the world scientifically, that it's causing structuring within the language that's less like their native oral form. That it's the expository form that is more like the English form. In other words, if we had Chinese tell a story and English tell a story, probably as a narrative, they're less alike. But the problem is that we are driving expository text down our students' throats so that by the time they come out of high school, they are fully formed with, well, maybe not, because they don't like to read anymore. But if they read, then they are more fully formed with an expository form of network structure. Remember the fundamental difference. Expository network structure tries to break down silos of information that should go together and form a bigger picture every time. Expository text is about understanding the endocrine system. So you keep making the endocrine system richer and richer and richer rather than keeping 5 stories about the endocrine system. But when you have a narrative, it's fundamentally different. You don't want narratives to mix together. If you have a story about saving a princess from a dragon and you have another story about saving a princess from a car accident, you don't want those mixed together. You want to keep them clearly in their own silo. It doesn't make any sense to talk about saving princesses as a concept. You get what I'm saying? So narrative by its nature tends to be siloed because of the contextual features such as place, time, and character that hold them together as a cohesive unit. Whereas expository text doesn't have cohesive units of time or space or character. They have some of that, but not much. So they're more likely to form the relational structures that are indicative of relational understanding. How are we doing time-wise? Are we out of time?
5:35.
It's time to stop. Okay, so how many thousand more slides do I have to go? Okay, so we didn't get to do, darn it, we didn't get to do anything with hands-on, but okay, so the idea is real simple, is that we're using, we used this in 2013, the graph centrality, because we were dumb and we didn't know what we were doing. And we got it from Freeman in 1977. So I got that, I put that article in our box if you want to look at it. And he talks about all these different ways that between the centrality has been used in all sorts of studies. It's very interesting. But what we're doing now is we're using Gephi and Node Excel, and we're generating the kinds of metrics that you see over here on the right. We're not just doing between the centrality anymore. We're looking at all of the metrics that are available from a network. So here's the same network represented in Node Excel. And Node Excel clearly identified 2 clusters, the bottom cluster and the top cluster, based on nothing more than the links that exist there. So maybe at some future date, we'll be able to look at Node Excel, but it's really easy to take pairs of nodes. What I meant to do, I'll tell you what, I'll make a 2-minute video using screen capture of how you go from CMAP tools into propositional pairs, and then how you copy those into Node Excel and push the button and it does these graphics for you. So it's a really, once you have a CMAP file that either an individual or a group has done, you can save it as propositions as text. Well, there it is right there. You can save the CMAP as propositions as text. You can enter those propositions into Node Excel directly, copy, paste. And then in Node Excel, you just say, show me the metrics, and it shows it to you. Okay. And then I won't get to Yu Wang's life map data, but she has got a, she created a CMAP, a mapping version with virtual reality goggles where the people put on the headset and they do mapping in space. And so that data generates XYZ data rather than XY data. So I was going to show you how we were analyzing XYZ data using the N by N array and doing it in Pathfinder Network, but there's no time to do all of that. So
X, Y, Y, Z?
I'm sorry?
How did you compare? X, Y, did you use X, Y, and Y, Z?
No, what happens is that as you're well aware, if you have XY data, you can get the distance by doing A squared plus B squared. Well, the solution in three-dimensional space is X squared plus Y squared plus Z squared, take the square root of that.
Okay.
It's just like the other, but it's with 3 variables rather than 2. And I did, in fact, in Box, put a file in a folder called, I think it's called Yu Wang in Box. I think, let me just go up to Box and see if I can find it. Yeah, it's called Yu Wang Virtual 3D Concept Maps. And there I have the conversion tool for XYZ. So it takes the XYZ data that comes out of the Affinity, out of the software tool, and then the Excel spreadsheet turns it into an N by N array and also gives you the PRX file. So boom, you put in XYZ, boom, you copy out the, oh, let me just show you this real quick because this is kind of cool. I'll show you just like 3 seconds of the video. So this is the person is actually creating their map here. Is that showing up?
Yeah.
Okay, so literally she created this tool so that, and she's got about 8 or 9 people that have done this already. So the map is there and they go over and they grab the concept on the left-hand side, they drag it out into the dimensional space and decide where they want it. And I think she's going to grab one, yeah. So you use of course, the tool to grab it. And so she's grabbing predictability. No, she's grabbing for he. Okay, she's got this one. So now we're trying to figure out how to move around now in the space. So I'm going, but this is the hard part. It's like driving a forklift. You don't know how to drive one until you've driven one for a while. And so now that she's trying to figure out, got to pull back. Oh, she's got to grab a connector. Okay, and then go back, and then figure out how to connect it to. And I'll stop this in a second, but okay, so we're going to connect it to traditional project management. Okay, so that's the idea. So there's a lot of learning curve in learning how to, but you can imagine, remember when we first learned how to use a mouse, that's probably before your time, but we all played solitaire. You played enough solitaire, then you can learn how to use a touch screen or a mouse. This is how you learn how to do VR. You practice doing things like creating 3-dimensional concept maps. Eventually you get real good at it. You just reach over, grab it, put it up there, boom, 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 comes automatic. But this software outputs the XYZ, and then we can analyze it with concept maps. So what we're doing is we're doing their 3-dimensional concept map compared to their 2-dimensional concept map, compared to their essay, compared to the expert map. And we can see, is there any advantage to doing 3-dimensional concept mapping compared to 2-dimensional concept mapping? And stop sharing. And okay, so I warned you I was going to do a lot of talking. Okay,